The terms disjoint and mutually exclusive are used interchangeably. Disjoint/mutually exclusive events are events that have no overlap in elements. In the example below, we are looking at event A and event B. Event A has 3 elements, which are underlined in yellow, and event B also has 3 elements, which are underlined in yellow. The reason why events A and B are disjoint is because there's no overlap in any of the elements seen in A and B. So to be clear, in event A, we have 1. Is there a 1 in event B? No. Is there a number 2 in event B? No. Is there a number 3 in event B? No. Likewise, if we look at event B, we see that there's a 4. Is there a 4 in event A? No. Is there a 5 in event A? No. And is there a 6 in event A? No. So this tells me that A and B are disjoint, which is also known as mutually exclusive. In notation form, we write this as A intersection B equals the null symbol, which is 0 with a slash through it. In the example above, if A and B are disjoint/mutually exclusive, that means they both can't occur. So if A occurs, B cannot occur. And if B occurs, A cannot occur. Probability can be noted as PR and then parentheses, or P and then parentheses. Probability can only take on values between 0 and 1. Typically, we see probabilities written as a percent. So for example, 20%, that can be written as 0.2, 90%, 0.9, 100%, 1, and then 0% is just 0. See how all the percents can be translated to decimal form? This is why we say that probability takes on values between 0 and 1. Now I'm going to go over 3 axioms of probability. So before I get started, I just want to remind you that S equals sample space and A equals event. So in axiom number 1, we see that the probability of A is between 0 and 1. Next, number 2, probability of the sample space S equals 1. And this means that an element of the sample space must occur. Number 3, for any infinite sequence of disjoint events, A1, A2, etc., we have the probability of AI, the union of AI from I equals 1 to infinity equals the sum of the probabilities of AI from I equals 1 to infinity. Sets is another word for events. Sets are mutually exclusive if the intersection between any two of the sets is the null. So in the example, we have AI intersects AJ, which equals the null for all I does not equal J. So to expand the example further, if we have A1, A2, and A3, and let's say that I equals 1 and J equals 2, then we have A1 intersection A2 equals the null, and 1 does not equal 2. To expand this further, we can pretend that A1 is an event and it has the elements 1, 2, 3, and A2 is another event with 4, 5, 6. Notice how there's no overlap in elements, which makes this statement right here true. If an event is impossible, the probability is 0. So the theorem that we're going to look at is the probability of the null set equals 0. And now we're going to prove it. So we're going to prove that the probability of a null set equals 0. Okay, so this example is from de Groot. Consider the infinite sequence A1, A2, etc., where AI equals the null set for I equals 1, 2, 3, etc. This means that each event A1, A2, A3 is a null set. Since each event is a null set, the intersection of null sets is a null set. So here we have null set, intersection with a null set equals a null set, which also looks like A1 intersection A2 equals null. Whenever the intersection of two sets is null, that means the sets, which are also known as events, are mutually exclusive / disjoint. Since we are looking at an infinite sequence, we can use axiom 3 to help us. Recall that axiom 3 states, for any infinite sequence of disjoint events, A1, A2, etc., we have the probability of the union of AI from I equals 1 to infinity equals the sum of the probabilities of AI from I equals 1 to infinity. For us, AI equals A1, A2, etc., and we know that the intersection of two of the events is null, which means that the entire sequence of events are disjoint. Since each event, A1, A2, etc., is null, we can say that the union of AI from I equals 1 to infinity equals the null. Since A1 union A2 is null union null, that equals the null. Using this information, we can expand on axiom 3. Okay, so here we have probability of the union of AI from I equals 1 to infinity equals the sum of probability of AI from I equals 1 to infinity. So remember that on the previous page, we showed that this portion right here is equal to the null, which is why we can write this. Okay? And then remember that early on in the problem, it indicated that AI equals the null set. So that's why we can plug in the null right here. Now, when we expand this right side right here, we're going to get the probability of the null plus the probability of null, and it's just going to keep on going. And the only way that this would be true is if the sum of the probability of all these null sets is 0. Therefore, this proves that the probability of the null set must equal 0. Okay, so now I'm going to cover 5 different theorems. So the first one, it says, for all finite sequences of disjoint events, A1, A2, all the way to AN, we have the probability of the union of AI from I equals 1 to n equals the sum of the probability of AI from I equals 1 to n. The next theorem is the probability of A complement equals 1 minus the probability of A. Next, if A is a subset of B, which can be notationally written like this, then the probability of A is less than or equal to the probability of B. Following that, we have the probability of A intersection B complement equals the probability of A minus the probability of A intersection B. And lastly, the probability of A union B equals the probability of A plus the probability of B minus P, the probability of A intersection B. It is important to know these theorems really well so that you'll be able to solve problems on a test easily. For any event A within the sample space S, which also can be written as A is a subset of S, we have the probability of A equals M over N, where M is the total number of outcomes in event A, and N is the total number of outcomes in the sample space S. So looking at this example below, it says roll a die 1 time. The sample space is S equals 1, 2, 3, 4, 5, 6. And each outcome is equally likely. Thus, each element has a probability of 1/6. So the chance of rolling a 1 is 1/6. The chance of rolling a 2, 1/6. 3, 1/6. Rolling a 4, there's a 1/6 chance that you're going to do it. If you were going to roll a 5, it's a 1/6 chance. If you're going to roll a 6, it's a 1/6 chance. Okay? So the probability of the sample space is equal to the sum of 1/6 from I equals 1 to 6, which equals 1. And this should look familiar because one of the theorems we learned earlier was that the probability of the sample space is equal to 1. Okay, so looking carefully at the 1/6, the 1 represents the total number of outcomes in the event of rolling a die once. Okay, and the 6 is the total number of outcomes in the sample space S. Okay, so let's look at the next example. Let event A be the event of rolling a 1 or a 6. Find the probability of A. Okay, so A has 2 outcomes, 1 or 6. So the probability of A equals 2, 6. 2 represents the total number of outcomes in event A, and 6 represents the total number of outcomes in the sample space S. An important note I wanted to point out is that independent events are not mutually exclusive / disjoint. And then before I close, I just want to share some properties of independent and dependent events. So first, looking at independent events, if you have the probability of A intersection B, that's going to equal to probability of A times probability of B. If you're looking at the probability of A given B, that's going to equal the probability of A. And the probability of B given A equals the probability of B. Okay, and then looking at the dependent event properties for probability, if we have the probability of A intersection B divided by the probability of B, that's equal to the probability of A given B. And then second, if we are looking at the probability of A intersection B divided by the probability of A, that's equal to the probability of B given A.